Um, Good morning, geometry, to our second lecture over 12-2 chords and arcs, page 771. I apologize for my lack of formal attire. It's actually 6:30 in the morning on Monday. My first video of this actually didn't upload super well to YouTube. So today, as I said, 12-2 chords and arcs, page 771 if you want to follow along in your book. Okay. So first thing we need to talk about is what's a chord. Not like an F chord in guitar or anything like that. A chord is something like this, where I take 2 points along the circle and I connect them. So it's just a segment with 2 endpoints on the circle. That's all a chord really is. The important thing is it doesn't have to go through the middle. It can go through the center. And if I did, say I had something like this, and I had this is still a chord, but more specifically, that would be a diameter. So we've talked about those before. And just a chord just means, again, just through 2 endpoints on the edge of the circle. They don't have to go through the center, but it can. It's certainly not against the rules or anything. So that's what a chord is. We're going to use that definition quite a bit here. So today is mostly theorems and otherwise just concepts, and then the homework assignment on that Math Excel for School website. Hopefully it doesn't get you guys too confused. So the first theorem, theorem 12-4, says that, let's see, if I have a circle, and let's say I have something like this, where I have A, B, C, D, and E, where E is my center. If angle AEB is congruent to angle CED, so if this angle here is congruent to this angle here, then, okay, just like most of my theorems, it's written as a conditional, if, then, arc AB is congruent to arc CD. Remember, arcs we do with that long stretch. An arc just means the distance around the edge of the circle. Now we can tell mine doesn't work exactly right. My angles are probably a little off, but in a circle case, those would be exact. Okay. So theorem 12-4 says if angle A is EB is congruent to angle CED, then the arcs have to also be congruent. Now the cool thing is, its converse works the same way. So the converse just says the, again, opposite direction. I can flip them. So if I already know my arcs are congruent, so if arc AB is congruent to arc CD, then angle AEB is congruent to angle CED. Okay. If I had the other direction, I still know that that one would work as well. Okay. So that moves us right into theorem 12-5. It's going to be a very similar drawing, theorem 12-5, and if I have my circle, and I have A, B, C, D, and I have my center E. Again, my center is probably a little off there, but you get the point. Now, my previous one didn't have anything to do with chords. This one just takes that idea and just turns it into a chord. So, if angle AEB is congruent to angle CED, then, again, another conditional, AB is congruent to CD. But this time they're not arcs, they are segments, or, as we see, chords. So, again, mine's a little off, this circle is a little smaller, but the idea stays the same, is if AE was in the center, and angle AEB was a fixed value, say 75 or something, some random number, and CED was the exact same value, those chords would be congruent. And, as you might have guessed, the same thing applies for the converse. The converse is also true. So, if we were to write the converse, if segment AB is congruent to segment CD, then angle AEB is congruent to angle CED. We would just eventually form congruent pairs of triangles. Okay. So, again, I told you we got a lot of theorems today, and that moves us right into theorem 12-6. So, theorem 12-6 does not really care about these central angles. I'm going to use the same drawing. I would encourage you to add a separate drawing just so things don't get too muddled. If my arcs are congruent, if my chords are congruent, so in this case, AB is congruent to CD segments, then my arcs are congruent. So in this case, arc AB would be congruent to arc CD. So if the chords are congruent, then my arcs have to also be congruent. And as you can expect by the pattern we've already established for our other theorems, the converse is also true. If arcs congruent, then chords are congruent. Okay. So what's happened already with our three theorems, just back to back to back, is if any of these are congruent, all have to be congruent. All have to be, and those we're talking about are those central angles, the arcs, and then the chords. As we've seen with this each iterate, we've had a relationship between the central angles and the arcs. We've had one with the central angles and the chords, and then now we just had the arcs and the chords. So if I have any set that are congruent, I know that all three have to be congruent. Interesting. Alright, so let's do one example here, I suppose. We'll just make sure we get a good circle this time. Sorry for messing it up. let's see, we got our circle. And then we have, let's see, example 1. Oh, I need 2 circles. Shucks. B, C, and D, F. So, my question is, if BC is congruent to DF, what else is true? So, maybe we need to label some circles here, so let's go with A, and then A, B, C, D, E, E. So, like we said, if one of those things is true, then all of them have to be true, right? And BC, as we clearly see, is just a chord. So, if my chords have to be congruent, then I automatically know that, 1, my arcs are congruent, and I also know that my angles have to be congruent as well. So angle DEF is congruent to angle BAC. I'll be right back here for a second. Sorry about that. A fellow teacher had a question. I didn't think I'd expect to run anybody at, again, when now it's 7:15 in the morning, but what can you do? Okay, so moving on into theorem 12-7. So again, I'm going to need a circle. Okay, so theorem 12-7 says that if I have chords, so if chords are equidistant, so equidistant spelled E-Q-U-I-D-I-S-T-A-N-T, equidistant from center, then they are congruent. Then congruent. So first, of course, I'm going to need a center. Now, equidistant from the center is exactly what you think it means, equal distance. Now, the way I know it's an equal distance is, remember the idea is the closest distance between any 2 points would be a line. Now, what also has to be true about that line is it would always be perpendicular, just like our heights. So I know that if I have 2 chords, the quickest and most efficient distance, my equidistance, would be perpendicular to both those chords. And I also know that, again, equidistance had to be the same. So, tick mark, tick mark. So, here, equidistance, then these lines are congruent. So let's say I labeled them. Let's see, AB and XY. So AB, the chord, so the segment AB has to be congruent to segment XY. Okay, that would be theorem 12-7. Now I believe that the converse is also true. It is. So, again, converse is also true. I'm not going to write out the converse just because I think I'm falling behind here on my time, but my converse would be if my chords are congruent, then they are equidistant. So, moving on to theorem. Oh, example, I apologize. Example 2. Okay, so again, I have a circle. And I got a center. That's not very center, is it? Okay. And if I have something like this, so I got AB, and then I got YZ, and I have my distances. Nine. And if I also told you that this cut this in half, where this value is 12.5. Yeah, that's fine. This is 12.5 for that piece. What is the length of YZ? Well, again, I get equidistance because I get the same value and I get perpendiculars. So I know that that's the shortest possible value. I know that the entire length of AB has to be the entire length of YZ, you know, assuming a perfect drawing, which unfortunately, again, this isn't our best one. So the entire length of YZ has to be the entire length of AB. So if AB right here, or AM, for example, is 12.5, and I get a tick mark, the entire length of AB would be 12.5 times 2, or 25 units. Which means, because AB is congruent to YZ, that YZ has to also be 25 units. Now all we have left are actually 3 more theorems. I know a lot of theorems today, but they're all very important. So we get theorem 12-8. So we get a circle. These are all going to involve a very special chord that goes through the middle, which, as we said earlier, is the diameter. So it's the AB. And let's say it goes through the center, so center C, for example. It says that, and then I also need something like this. And I'll use X and Y again. So, if diameter, so if my diameter is perpendicular, remember that's symbol for perpendicular, upside down T, perpendicular means it forms a right angle, which it does. If diameter is perpendicular to a chord, then the chord is bisected. So again, what does bisected mean? We've talked about that way back previous geometry terms. Or bisected just means to split in half. So if I had this value was z, I would know that xz would be congruent to zy because that is bisected, because again, AB is a diameter that meets that chord at a right angle. It is perpendicular. Theorem 12-9 actually goes off the same concept, except it is the converse. So earlier we had converses where they weren't their own individual theorems. This one's important enough to where it is. So theorem 12-9 says that if chord is bisected, let's see. By a diameter, then they are perpendicular. So if I already have these x, z is congruent to zy parts, and I know that AB is a diameter, then I get the right angle part. And then theorem 12-10 actually again goes with the same idea. So theorem 12-10. So here in this first one, I was given the part that diameter, perpendicular, so then I know the chord's bisected. Here I was given the bisected and perpendicular diameter, then perpendicular. So if I know that if chord meets a perpendicular bisector, then it's the diameter. So these three theorems, 8, 9, and 10, all go together. Basically, you're given two pieces, you automatically learn the third. So again, the first one, we were told diameter and perpendicular, so then we know bisected. Our second one, we knew bisected diameter, then we know perpendicular. And our last one, we were given perpendicular bisected, then we know diameter. You know two of them, you'll automatically know the third has to be true. That's why these ones are all clumped together, and I need the same drawing for all three. Okay. Keep working on your homework online, and if you have any questions, again, feel free to email me. Thank you.